Hello and welcome to the first lecture of week 10 of the course Introduction to General Relativity. Alright, let's look at the agenda for today's lecture. First, we're going to look at the gravitational disturbance emitted from a source, and we will conclude this by looking at the quadrupole formula, and I will be very schematic about the derivation. Not all the steps will be included. People who are interested in the derivations, please look at the lecture notes. This is mostly algebra, which I will skip, so I will be very schematic. Okay. The important point as I was mentioning is that this formula will show that the gravitational disturbance emitted from a source will depend on the quadrupole moment of the stress tensor of the energy density. And once we have this quadrupole formula, we will compute the energy and power of the emitted gravitational quadrupole radiation. Then I will consider an example which has been historically significant, which is the binary system, or technically speaking, a rotating quadrupole. Studying these kind of systems led to the indirect detection of gravitational waves before, of course, the current generation LIGO laser gravitational wave detectors came into play. We were able to indirectly infer the existence of gravitational waves by studying the binary systems. Let's look at gravitational radiation from sources. So, in the previous lecture, we looked at gravitational plane waves. That is, first of all, we were looking for solutions of this equation, which, as you know, is the linearized field equation in Lorentz gauge. And I've put the source term to 0. The reason is that we were looking at gravitational disturbance far from the source. And as you know, far from the source, the wavefronts become more and more plane-like. So that's why we were interested in looking at plane waves. This is it was illuminating, but at the same time, you do not get any information about the source because we are studying it far from the disturbance which has produced it. Now, as you are closer to the source, the wavefronts will be more like spherical surfaces or compact closed surfaces. So we are interested in this regime. So this lecture we will include the effects of the source. That is, we will turn on the right hand side of the field equation, box h bar mu nu effects. So let me remind you, this h bar mu nu is not the metric perturbation, but it is something which we defined as to be the trace reverse perturbation. The trace reverse perturbation is related to the metric perturbation by a linear redefinition. H mu nu, which is related to h bar mu nu, is related to the metric perturbation h mu nu in this way. F eta mu nu, h bar, which is not the metric perturbation, but the trace reversed perturbation. Right? So the box operators, as usual, is the D'Alembert-Borchin in flat space because we're operating in the weak field regime and the metric can be considered mostly Minkowskian. And then kappa, this constant, is a short form for the, I believe, 16 pi g Newton over c to the fourth. So now we are studying non-vacuum solutions to Einstein general relativity or linearized Einstein general relativity. Okay, so last lecture was the vacuum solution. Now we have a source turned on, so these are non-vacuum solutions to linearized GR. Now, as I said, that because we are solving an equation which has T mu nu on the right hand side turned on, so the solution will naturally contain information about the source. And we will solve this. Okay, so that is, we will still first solve for the perturbation where the source is a unit point source given by the Dirac delta. And of course, when you solve a boundary PDE, you have to provide boundary conditions to determine the solution uniquely. So we will solve this Green function subject to appropriate boundary conditions. And then the general solution, that is the source solution for a general source, will be given by this convolution. Okay. All right. So This Green function, I'm not going to do a derivation because this is the same Green function which you have encountered in classical electrodynamics, especially postgraduate course in classical electrodynamics, where you derive this. So this Green function, I will just write it. So I have highlighted three parts of the Green function in three different colors. There is the blue part, which is the 1 over r, as you can imagine for a unit point source. There is a 1 over r fall off. But I will point out first to this in purple font, there is this Heaviside step function, which is telling you that this is non-vanishing. In fact, it is equal to +1 when x naught is greater than y naught. So x is the point at which we're observing, or the field is, and y is where the source is located. So it is telling you that the time at which we are making the observation, sorry, not here. So let me just where we're observing the field point and the source is somewhere here. Now it is telling you if this is the vertical direction is the time direction, then x is greater than y, meaning the signal is coming out of the source is located in the path of the observation. Right? So this kind of Green function, where the source is in the path of the disturbance of the field, is called a retarded Green function. It propagates data from past to the future. And secondly, now I want to focus on this part with Dirac delta function, which is in solid form. This is telling you that x0 minus y0 is given by the same as the spatial separation. So the time separation is equal to the spatial separation. That means x and y are light-like separated. So in particular, y is light-like separated from x in the past direction. So the Green's function has non-zero support on the past light cone of x. Okay, on the past light cone. Not inside, not outside. Okay, just on the surface of the past light cone. And physically, we understand why this is the case. The disturbance which propagates from the source to the field point propagates at the speed of light. We know that gravitational waves or gravitational disturbance is propagated at the speed of light. Hence, any Green's function which will propagate from the source to the field point must lie on the path light cone of the observation point. Alright, so we will plug this in and perform the integral. In particular, we will do the time integral. If we do this, I'm sorry, the y0 integral. If we do the y0 integral, the answer is this. So this x minus y in the denominator, the spatial separation is this from here. And then the step function and the Dirac delta function can be integrated when we integrate over y0. And once we do that, we have this result. Again, people might be getting echoes of electrodynamics because you write exactly the same formula for the potential, which we call the retarded potential. Here, we can call this the retarded phase reverse perturbation. And in electrodynamics, instead of T mu, you would have J mu, which is the current density 4 vector. And then it tells you that the current density 4 vector has support in the retarded time. So you can recognize this combination as the retarded time, T sub r, from electrodynamics. And so this is the general solution, of course, and the general solution can be, we have written down the general solution, which is good, but it is not that insightful. So we should specialize for various cases. In particular, you can take a situation in which there is no dependent on x naught, that is, it's a static source, and you can get the solution for that static source. The solution will also be static, that is, no time dependence. But those are not interesting solutions for us. We are interested in the case when the stress energy momentum, that is, the matter is distributed in such a way that there is an oscillating component or a fluctuating component. And we want to study what is the disturbance which is produced as a result of this fluctuation. So typically, as is what is done in postgraduate electrodynamics courses, if you remember your postgraduate course, is that we will switch from time domain to the frequency domain by performing a Fourier transform in time. So, I'm sorry, there's a typo here. This should be F. Switch from time domain to frequency domain. So, this is the trace reverse perturbation in time domain, and then I've taken Fourier angle of that and obtained the frequency domain trace reverse perturbation. And so we have to do that for both sides. So this is just for the left hand side. You have to perform the same Fourier integral on the right hand side, especially for this t, because this is where the x0 dependence is. Remember, x0 and t are the same thing, a modular factor of c, as usual. And this is the frequency domain solution, which I've written in olive fonts. And as you can see, the difference between these two is that, of course, the time dependence on the source has gone and replaced with the frequency dependence. And because of this difference, we actually get a phase factor here. There was no such phase factor here. In the time domain formula, you just had a 1. But in the frequency domain, you have a phase factor. And this denominator goes through unchanged, of course, no difference. So, again, this is the general formula in frequency domain, which is not right away very insightful. But we are going to make a couple of approximations, simplifying approximations, which will get us more leverage. So, first approximation which we will make is that the radiation is being observed far from the source, such that, so this is a typical situation. We have an astrophysical source, which is perhaps light years or parsecs away, and for all intents and purposes, we can think of the source as a point object from Earth when we observe it. So the separation between the Earth and the various points on the source will not vary significantly over the source because it is pretty far away. So this separation, I can take the separation from the source to any point of the separation from the observation point to the source will almost be the same through all over the source. And so approximately x, which is r. Okay, I'm denoting that separation by r. And the second approximation is that the source is small compared to the wavelength of the disturbance. Okay, so if I consider this to be the wavelength, the dimensions of the geometrical dimensions of the source is much smaller compared to the wavelength of the source. Or, in other words, the light crossing time, that is the time light takes to cross through the source, is much less than the time period of the fluctuation, omega. Okay, omega inverse is much larger than the y over c, which is the light crossing time. Okay, so this is the long wavelength approximation. Okay, so these pair of approximations or simplifications that we call the far field of the radiation zone approximation. All right. So then the solution, of course, simplifies because as a result of this, these two approximations, I can pull out these two factors out of the integral. So because x minus y is not depending much on y because it's far from the observation point, so I can pull out the denominator. And because the geometric dimensions of the source is smaller than the wavelength, this phase is almost same throughout all over the source. So this can be also, when we perform the integral over the source, this phase can also be taken out of the integral. What precisely what we have done, the phase is out of the integral, and the factor of r, the denominator, is also out of the integral. Then we are left with a simple volume integral of the frequency domain component of the T nu of the source. Okay, this is the solution in this radiation zone or far field approximation. All right, which is true for most astrophysical situations, where it is light years or parsecs away, and these are appropriate approximations to make. All right, so as I was mentioning, this solution must also satisfy Lorentz gauge. Remember, we only obtained this equation in the Lorentz gauge, so one must make sure that this solution also satisfies the Lorentz gauge condition. Again, because we are working in frequency domain, the Lorentz gauge condition, which is given by this 4 divergence of the trace reverse perturbation vanishing, we have to express this in frequency domain. And when we go to frequency domain, these derivatives will get converted to because of the exponential factor in the Fourier integral, this will be converted into factors of omega. So remember, this Lorentz gate condition is a vector condition, because although mu is a summed over index, it's the domain index, nu still is the free index, and we can consider two cases: when nu is space-like and when nu is time-like or zeroth component, which gives us two conditions, these two. And the reason, one advantage of doing this is that we find that the I0 component and the 0,0 component of the phase reverse perturbation can both be expressed as derivatives of the Ij component. The I0 component is proportional to the first order spatial derivative of the Ij component, and the 0,0 component can be shown to be a second order spatial derivative of the Ij component. Okay, and this is just a consequence of Lorentz gate. So, as I've mentioned at the punchline, Ij component of the trace reverse perturbation determines all other components, the 0,0 and the I0. So, we will not solve for the general case, but just for the Ij component, Tij. Alright, and the next set of manipulations would be to convert this Tij into moments of the T00, that is the energy density. Sorry, Yj T00. We will use energy conservation of stress energy momentum tensor, the continuity equation for it, along with some other identities, and convert this Tij into moments of the energy density. So let's look at that. So first of all, as I said, that we have the continuity equation for energy conservation, which is given by delta T mu equals 0. In frequency domain, we have to write it in these formula, and then we will use a couple of useful identities. I will leave the details for the notes. I will spare you the details. They're not very illuminating or insightful. All I want to highlight is that the Ij component of the source, which we will need, because we have to perform this integration here. So we need the Ij component of the stress tensor of the source, which are the various pressures and shearing stresses. That can be written as this total derivative, total spatial derivative, plus some moment of the 0i or the 0j component. And further, a second identity will allow us to convert the moment of the 0i components in terms of another total derivative term and a second order moment or quadratic moment of T00. Okay, so ultimately Tij will be related to the second order moment, Ij moment of T00. Alright, so there are a couple of useful identities which we will use to accomplish that. Okay, once we are done with that, we can write down the phase reverse perturbation in frequency domain in the radiation zone, and it will turn out to be given by this formula. So as you can see, there is an omega square factor here, and there is this Qij, which is the quadrupole moment of the energy density of the source, T00. Okay, as you can see, so it's a second order moment integrated all over the source, T00. Okay, so this is the quadrupole moment. Now, y equal to 0, the point y equal to 0, we can choose to be the center of mass of the source actually. So, if we do the Fourier transform back and go to the time domain, we get the famous quadrupole formula, which tells you that the phase reverse perturbation at x is related to the second order time derivative of the quadrupole moment of the source evaluated at the retarded time. So here in the retarded time, I do not have x minus y, the separation between the spatial separation between any point on the source and the field, but we have the center of mass, the separation from the center of mass. So the phase reverse perturbation is proportional to the second order derivative of the time derivative of the quadrupole. Okay, if you have a static source, of course this is 0, but let's say there is some oscillating component or time dependent component, which is given rise to the solution. All right. So this is, I would encourage you to contrast the situation with the corresponding situation for electromagnetic radiation. There you have a dipole formula. The potential is proportional to the first order time derivative of the dipole moment, if I remember correctly. So contrast that. Here the leading term is not a dipole term, but a quadrupole term. And as I mentioned before, in general relativity, we do not have dipole radiation because having a fluctuating dipole moment of mass would mean that the center of mass of an isolated system, then the source is moving. But for an isolated source, we know the center of mass cannot move. That would violate conservation of energy momentum. So we do not have a dipole radiation in general relativity. The leading order contribution is directly the quadrupole formula because the dipole moment can never fluctuate. All right, so this is the quadrupole formula, which is one of the highlights of this lecture. And once we have that, we can ask, okay, this is the disturbance. What about the energy which is being transported by the disturbance? For that, I will quote a result from classical field theory, which is beyond the scope for this course, so we will not do a derivation of this. But people who are curious can look at Appendix A2 of Ohani and Ruffini's textbook. They have an appendix in which I feel is pretty self-contained and tells you how to do this derivation using methods of field theory, classical field theory. There you can show that if you have the metric perturbation. So now I don't have the bars over the edges, okay? So the edges bars are gone, so that means I'm talking about the metric perturbation. Given a metric perturbation, how to compute the stress energy tensor. That is something which you do in classical field theory. You start with the Lagrangian for the H. That is, in fact, this is nothing but the linearized Hilbert action, Einstein-Hilbert action. And once you have that, and you have translation symmetry, classical field theory tells you how to compute the corresponding conserved current, T mu, and the expression is given by this. Okay, so I will not do this derivation as I said. I will refer to those who are curious. I can refer to Appendix A2 of Ohani and Ruffini. And this is not the full answer. I've dropped certain terms which are zero because we have Lorentz gauge condition. So this is not the general gauge answer. This is a gauge fixed answer in the sense that I've already chosen Lorentz gauge, and in Lorentz gauge, the stress energy momentum tensor for the gravitational disturbance looks like this. All right, and at this point, I would encourage you to take the static limit of this expression, in particular the 0,0 component. Look at the T00 component for the H, so the gravitational disturbance H. And if you do that, you will see that you get back the expression for the energy contained or energy density in the gravitational field in Newtonian theory. Okay, if you remember the lectures on Newtonian gravitation, there was some discussion about the energy contained in the gravitational field. And there, of course, we did it in a very hand-waving manner, but it would be assuring, as I promised at that time, that this expression will be justified when we learn the relativistic theory. And sure, here you can see that indeed, this is the energy contained in Newtonian gravitational fields. All right. Next thing, I would like to remind you that when we discuss the very important quantity called the stress tensor, that various components of the stress tensor represent various different things. The 0,0 component represents energy density. The 0I component represents the fluxes, energy fluxes, that is the energy per unit cross-sectional area per unit time in a given direction. I0s are the momentum densities, and the IJs are the shear and pressure. All right, so because we are interested in how much energy is being carried by the gravitational waves, we are naturally interested in the 0I component. Okay, let's say we consider an area element orthogonal to which the energy, orthogonal to which the energy is being transported, and let's say it is given by the direction n hat, and let's look at the energy being transported amount of time given by delta T. Then this is, of course, the flux, and then the energy that is being transported will be proportional to how much cross-sectional area there is to cross through, and how long we allow the energy to transport. So this is the flux multiplied by area multiplied by time. That gives you the energy transported. Now we can have, given a localized source, what is the total energy transported, right? Total energy transported over all solid angles. So the total power radiated. So we will divide both sides by delta T to get the power, and then integrate it over all solid angles, right? For that, I have to write so the energy is obtained at this point R, that this area element is located. The solid angle is obtained is d omega, and R is the distance between the source and the field, of course. So this integral we have to perform, then we get the total radiated power. And I will do the integral, I will spare the details, but if you plug this, again you consider the zero I component here, and perform this integral, then you see that the power is given by the third order derivative of the quadrupole tensor, quadrupole moment, square of that. Okay, there are two factors, and ij indices are all dummy indices, they're contracted with each other. And this tau is the famous retarded time. Okay, retarded time. And then there's some numerical factor, which is there for dimensional reasons. And of course, because this is the leading order, we get a contribution from G Newton. Alright? So T will contain 1 factor of inverse G Newton, and 2 factors of H will give you 2 factors of G Newton in the numerator. So upon cancellation, you're left with 1 factor of G Newton. Okay? So this is a very important quadrupole radiation power formula, that the power of the emitted radiation is proportional to the square of the third time derivative of the quadrupole tensor. Okay? This is a very important quadrupole radiation formula. Again, I would encourage you to contrast the case with electromagnetic radiation, where the radiated power is proportional to the square of the second derivative of the dipole moment. Okay? Not the quadrupole moment. And now let's look at an example. All this is very abstract formula, so let's bring it home by looking at a special system, which is a binary system, or what we will call a rotating quadrupole. What we have here is 2 objects which can be stars. Both of the stars are neutron stars, or a neutron star and a white dwarf, or a neutron star and a black hole, so long as we have just 2 objects. So, and they are orbiting each other with around the common center. So we have 2 orbits, and then there are 2 objects which are going along in these orbits around the common center. Okay, both of them have a common center, which is this point. Oh, okay, so they're going around this common center, and we will make some simplifying assumptions in order to simplify the analysis. First, we will ignore the dimensions of the stars of the objects compared to the dimensions of their orbits, so they're like point objects. And these point objects are point masses, with masses M1 and M2. And I'm also going to assume that the orbits are circular, with radius A1 and A2. And finally, I'm going to assume that the speeds are non-relativistic, so the equations, the dynamics, the classical mechanics of the thing is entirely Keplerian. So these are Keplerian orbits. And the common frequency of this would be, in that case, given by this formula, omega, which is the orbital frequency of this, is given by G Newton, square root of G Newton times M over R cubed, where M is the total mass and R is the separation between the two. Okay, so if A1 is the radius of this orbit, and A2 is the radius of that, so the objects are located here and here. diametrically opposite. So this is going to be the case. Okay, and this is the common center of mass. Now, given this, from the form of the orbits, which, as I said, you assume that they are Keplerian circular orbits, one can easily compute the energy density. Energy density is given by mass density times c squared, which is from the same formula, E equals mc squared. And the mass density for point objects are given by Dirac delta functions, which we studied in electromagnetism, so I don't need to repeat this. So this will be the stress tensor, and this, because there are 2 point masses, we need to sum over 1 and 2, rho I. So this index I, if plotted to the note here under the sum, is summed over 1 and 2. And once we have the T00, we can compute the quadrupole tensor matrix, which is given by this formula, right? And the integrals will be very easy because the mass densities will be Dirac deltas, right? They are point objects, so the densities are given by Dirac delta, and integrating Dirac delta is very easy. Alright, so this computation is fairly easy. I will leave this details of the computation for a homework exercise. Please do that. Please go through the steps. And then once we have the Q, we can directly use the formula that the power of quadrupole radiation is proportional to the square of the third order time derivative of the quadrupole moment. So if you plug in chart, then what you get is that the radiated power is proportional to the fifth power of the mass, and inversely proportional to the fifth power of the separation R. Okay, so this is something we take. Rest of this proportionality constant, rest of them are G Newton and some dimensional factors of C and all that, universal factors, pi's and c's and all that. So I'm not going to be bothered by that. So, but the important physical thing is proportional to the fifth power of the mass and the fifth power of the inversely proportional to the fifth power of the separation. Okay, so clearly, because it's the fifth power of the separation, unless the separation is very small, the radiated power won't be large. In particular, let's consider the best case scenario when the masses are very heavy, that is, they're white dwarf or neutron star binaries, where the masses are of the order of 2 solar masses. Let's say both of them are very heavy. And let's say the separation is like 10 to the power 5 meters, which is about the, I think, almost the distance from the moon to the Earth, something like that. A small separation, these two are orbiting each other. So in these cases, the power radiated would be large, but still, for the vast majority of cases, the radiation will be too weak to detect on Earth. Remember, Earth is very far from these, and for the vast majority of cases, these are very difficult to detect. In fact, the radiation is far too weak. However, this was the status quo some decades back. Now, of course, we have these excellent interferometers, such as LIGO, in which even this weak radiation can be detected. But there was a time in which this radiation flux was too weak to detect directly. In that case, there was an indirect detection method in which people track the binary system itself, because if the significant amount of energy is being emitted, that would lead to loss of energy and angular momentum in the system. As a result, the orbits will start changing, and this change in the orbit should be observable if one studies the evolution of the binary itself. Okay, of course, for the orbit to be observable, these two have to be very bright sources. Of course, we cannot have very bright sources if you have just stars. They're not very bright, but we can have binary pulsars. That is, when one of the stars or one of the objects in the binary system is a pulsar. A pulsar is a neutron star which emits periodic pulses, regular pulses, and those are in the radio frequency range. And those radio waves can be picked by radio telescopes, of course. And from those pulses, we can get an idea about their orbits, okay, orbits and periods and all that. So the first binary pulsar which was detected was a game changer. So this was in 1974 by this gentleman Hudson Taylor. This is called PSR 1913 plus 16. The PSR is just the short form for the word pulsar, and these are actually coordinates in the sky, the location on the celestial sphere. So this first binary pulsar which was detected was a game changer, because now we could study the binary system using the pulses emitted by the pulsar. And when we apply general relativity to this system, due to the loss of energy, the orbital period will decrease. Okay, the orbital period of the binary system, which would lead to the orbital emission of the pulses. So for every orbit of the system, there will be 2 pulses, because and this observed decline in the orbital period was found to be in excellent agreement with general relativity, with the predictions from general relativity. Of course, again, I'm sparing you the details. The details can be found in Ohanian and Ruffinius section 5.5, these pages. They do a thorough discussion of the experimental details, technical details, which I'm omitting. But the important thing to know is that the observed decline in the orbital period, because of loss of energy, it was losing angular momentum, and the period was shrinking. That was found to be in excellent agreement with. So please refer to Ohanian and Ruffini for the details. And we will stop our lecture here. So let's give a summary and provide an outlook for our lecture. So we studied non-vacuum solutions of linearized general relativity. And the subclass of this, which we were interested in, were gravitational radiation emitted from sources, which were fluctuating component of energy momentum tensor. And then we studied the general solution using the retarded Green function method, with the same trick which is used in studying electromagnetic waves. And further simplifications were done in the far zone approximation or the far field approximation. And that led to the famous quadrupole formula for the trace reversed field in terms of the second order derivative of the quadrupole moment of energy of the source, second order time derivative. And once we had that, we computed the power of the emitted quadrupole radiation. As I said, this required us to have some knowledge of the stress tensor for gravitational disturbance, which is usually taught in a course in classical field theory, which is beyond the scope of our course. So I just quoted some results. But anyway, if you use those results, you can compute the power of the emitted quadrupole radiation. And the signature of this was that the power is proportional to the third order time derivative of the quadrupole moment. Third order time derivative dot dot dot, 3 dots, and then this quantity squared. Okay. And then we looked at an example, which was gravitational radiation emitted from binaries, which are 2 celestial objects orbiting each other around their common center of mass. And this example I chose, you have studied many different examples where you have different kinds of fluctuating quadrupoles, but this is particularly what is called a rotating quadrupole. Because this was significant in history, it provided us with the first indirect detection of gravitational waves, of gravitational radiation, which is the Hudson-Taylor pulsar binary. And up next, we will look at the vacuum solution of fully nonlinear Einstein field equation. This was the original agenda for week 10, but as I said, this material we discussed in today's lecture is a spillover from week 9. But original intent was to study the fully nonlinear Einstein field equation on week 10. And we will in particular look at solutions which have spherical symmetry. And this will turn out to be the Schwarzschild solution. Okay, this is the first nonlinear solutions to general relativity which was written down within I think a month of Einstein proposing the equation. Schwarzschild came up with the solution. So we will look at this in the next section. Thank you very much for your attention, and I'll see you in the next section.